All right, we've got just a few seconds before it's official start time. Welcome back, everybody. I'm Dina Weibel. Here is your 12:30 session of Roger That. This is Andy Calloway from the Johns Hopkins University Applied Physics Lab. He is the Flight Operations Manager for Dragonfly and experienced mission operations manager for space missions, including OSIRIS-REx and Messenger. And he's got 30 years of experience in space mission operations. His most recent flight project was as a missions operations manager, or MOM, of OSIRIS-REx from April 2016 through proximity operations at asteroid Bennu, culminating in sample collection and stow in October 2020. And I remember that day well when it landed. Andy's current project is Flight Operations Manager for Dragonfly, which launches in July 2028. He also supports Europa Clipper instrument teams part-time. Andy has contributed to numerous missions, including Messenger, New Horizons, and is it pronounced TRIM?
TRIM, that's right.
Okay. And he's
Tropical Rainfall Measuring Mission.
very cool. And a member of the principal professional staff at Johns Hopkins University Applied Physics Lab. Thank you very much and welcome to Roger That, Andy Calloway.
Absolutely. Thanks for having me. It's a pleasure to talk about this wonderful mission. I was the operations manager, as you can see on the bottom there, for about 5 years, from the year of launch all the way through the tag, what we call touch and go sample collection. And then in 2021, I returned back to the Applied Physics Lab. I was actually on loan for those 5 years to the management team at the NASA Goddard Space Flight Center. So I actually had 2 offices for a while, one over there and one at APL. So anyway, my talk today is just an overview of the mission, just kind of from the insider's perspective and some of the challenges we had to face and how we overcame them. So I guess I can jump right in, right? Okay, so we love our acronyms, of course, on NASA missions. OSIRIS-REx is no exception. This particular acronym was the brainchild of our principal investigator, Dante Loretta. And you can see what the letters stand for here. Origins, because we were tasked to return and analyze a sample of pristine carbonaceous asteroid. The SI is Spectral Interpretation. RI is Resource Identification. S is Security, and the RE was Regolith Explorer. So pretty clever. And you'll see later this mission was repurposed after we brought the sample back from asteroid Bennu, and so we modified our mission name at that point. All right, so asteroid Bennu, you can see the original nomenclature at the top there. I'll talk a little bit later about how Bennu got its name, but it always starts off, with a classification like you see. Bennu is a primitive asteroid from the very beginnings of our solar system. It's called a B-class asteroid, carbonaceous, meaning it's volatile rich. And up to this point, we had never visited this type of asteroid before. And its size and shape and rotation were characterized by Arecibo. A lot of you remember that wonderful observatory before it came crashing down out there in Puerto Rico. You can see from the images, all we really knew back then was just this kind of really fuzzy view, which came, of course, to life when OSIRIS-REx arrived. And so we had just this very coarse shape model that you see on the right that had this kind of spinning top shape. But other than that, it was featureless. We just didn't know much about that. And so obviously studying any asteroid that crosses the Earth's orbit, what we call potentially hazardous asteroids, is strategically important to NASA. Just a few milestones. Well, we launched back in 2016 on an Atlas V on September 8th. These kind of planetary missions, usually it's a combination of what we call gravity assists or planetary flybys and what we call deep space maneuvers, which is really a large delta V trajectory adjustment that we have to do. And OREX, which is what we kind of shorten our name to, we call it OREX, was no exception. And so we conducted our first big DSM at the end of the year of 2016. And then we had a part 2 that we did not quite a month later on January 18th. When we work in mission operations, we have a navigation team that supports us for all of our maneuver planning and trajectory analysis. And for this mission, the Kinetics Corporation was our prime nav contractor. And then we had a backup nav team based out of Goddard Space Center. We had a unique opportunity because of our position in the inner solar system to do a Earth Trojan search. These are kind of fictional at this point, asteroids that might exist within the orbit of Mercury if there's a stable area there before they would get burned up in the sun. And so we did a survey, and of course we did not find anything that would have made a lot of headlines if we had. But it was kind of a win-win because we were able to do those planning activities in the same way that we would later do for our natural satellite searches. You can imagine when you're on an exploration mission like this and we're going to a new place like an asteroid, we want to make sure that there are no hazards or natural satellites, because some asteroids actually do have a smaller moon around them. We did have one issue that we encountered during our cruise phase of the mission, and the navigation team first noticed this. It's what's called outgassing. So molecules that are like baked into the fabric of our sample return capsule would basically leach off of it when it gets exposed to the sun. And over time, that can actually impart a small, very tiny change to the attitude and trajectory of the spacecraft. And despite all our best efforts before launch, to bake all that out, were some surfaces that surprised us. And so we had to come up with some special flight activities where we would maneuver the spacecraft a little bit to point different sides of the spacecraft to the sun to essentially bake off those molecules so that they wouldn't affect us later when it really mattered. So that was kind of a surprise, but a fun challenge that we overcame. And then, as I mentioned earlier, our Earth flyby was on September 22nd of 2017. And one really good piece of news, of course, we have a lot of extra fuel on board just in case we need it, but our approach maneuvers to asteroid Bennu were pretty much flawless. And because of that, we were able to basically recoup all that saved propellant and then use that later in the mission for extended mission. So that was really wonderful to be able to do that. All right, proximity operations, what we call prox ops. So it was 2 years once we got into that prox ops phase. And each phase of proximity operations was very unique and challenging. And so you can see just a list here. We had kind of some fun names that we gave to these different phases of the mission. And I have a YouTube video that kind of shows each of these phases in a graphical form. And so over those 2 years, we did the ones that you see on the screen. And you'll see in a minute, we had a huge surprise when we finally got close to Bennu, close enough to image it. And that required us to add some new observations to this timeline that hadn't been originally planned. And so then we had, of course, our touch and go, which most of you hopefully are familiar with. And then we actually did one final flyover of the touch and go site just to get a glimpse of how we might have changed it. And then we returned home. All right, so let me get out of full screen here and switch over to the video. And hopefully you will be able to hear this. If you don't, Deanna, let me know and I'll recheck the box again.
Okay.
Bennu, one of Earth's closest planetary neighbors.
Okay. Here.
An asteroid roughly the height of a skyscraper. A remnant from the dawn of the solar system, made of carbon-rich rocks and boulders. And since late 2018, the place that NASA's OSIRIS-REx mission has called home. When OSIRIS-REx arrived, it began wrapping Bennu in a complex web of observations, starting with a preliminary survey of its size, shape, mass, and spin. On New Year's Eve, OSIRIS-REx was captured into orbit by Bennu's minuscule gravity, making it the smallest world ever to be orbited by a spacecraft. In early 2019, it broke orbit to conduct a detailed survey. A series of sweeping passes allowed OSIRIS-REx to study geological features at different latitudes and times of day, enabling stereo imaging and landmark-based navigation.
It's quite the
During the
spider web,
detailed
isn't it?
survey, OSIRIS-REx globally mapped Bennu at only 5 centimeters per pixel, the highest resolution of any planetary body, including Earth. On June 12th, the spacecraft entered a new orbit at an altitude of just 680 meters, setting another record and establishing a home orbit for the remainder of the mission. In September, it began reconnaissance on 4 candidate sample collection sites, potential locations on Bennu to touch down and collect a sample later in the mission. OSIRIS-REx concluded its first year at Bennu back in orbit, circling the asteroid's terminator, or boundary between day and night. Here, outside forces acting on the spacecraft are balanced, allowing it to orbit within the same plane over time.
We actually call that a frozen orbit.
Reconnaissance resumed in early 2020 with close flyovers of the primary sample collection site Nightingale and the backup site Osprey. In mid-April, OSIRIS-REx performed the first of 2 rehearsals prior to sample collection. It navigated to a predetermined checkpoint about 125 meters above Bennu, then descended to within 65 meters before backing away. After the checkpoint rehearsal, OSIRIS-REx flew one final reconnaissance sortie over Site Osprey. Then it made a series of high-altitude maneuvers while rebooting its onboard processor and preparing for its second rehearsal of the sample collection event. On August 11th, OSIRIS-REx departed its home orbit and made a 4-hour traverse to Bennu's northern hemisphere, retracing its earlier path. After performing the checkpoint engine burn to begin its descent, it made a second engine burn called match point to match Bennu's rotation before backing away at an altitude of approximately 40 meters. Now, the most crucial moment of the mission had arrived. On October 20th, 2020, at approximately 11:30 a.m. Mountain Time, the spacecraft departed orbit. A few hours before, mission controllers on Earth had sent the commands for the touch-and-go sample collection maneuver, or TAG. As they watched with anticipation, OSIRIS-REx steered itself to sample site Nightingale, maneuvering toward the small crater at the walking pace of a spider. At 4:11 p.m., the mission received confirmation. OSIRIS-REx had touched down and collected its sample. Following TAG, the spacecraft drifted to a safe distance away from Bennu. By the end of October, mission controllers determined that it had exceeded its goal of collecting 60 grams of asteroid material. They directed it to stow the sample in preparation for return to Earth. Before departing Bennu, OSIRIS-REx was given one final task. On April 7th, it flew over Site Nightingale to observe how the sample collection event had changed the surface. And with that, OSIRIS-REx had recorded its mark on Bennu and spun the last strand of its web.
Okay, let's switch back. Oops, I gotta switch here. All right, so you can see from that movie how convoluted, if you will, our 2 years of operations were. It was pretty much nonstop. We had to come up with a lot of clever ways to conduct so many maneuvers and to try to do it mostly on day shift so that we didn't have a huge team that we had to try to fund. So we actually were able to come up with some really clever ways working with our Deep Space Network partners. They're the ones that have the antennas around the world in Goldstone, California, in Madrid in Spain, and Canberra, Australia. That's how we communicate with the spacecraft. And you saw right before the tag, we had that rehearsal that we did, and everything went so smooth with that rehearsal. We all really wished we had just kept going and actually done it there, but of course, everything was not pre-programmed for that. So that was the biggest surprise of the mission. It wasn't just a sandy beach when we arrived. It was all littered with boulders and rocks, but that wasn't the only big surprise. So I was actually there on the weekend. I was at Colorado Springs at Garden of the Gods, and I got this phone call from our operations team that we were starting to see strange objects in our images. You can see this kind of compilation image on the right. And it turns out Bennu is what's called an active asteroid, where various forces, including solar radiation pressure, micrometeorite impacts, and so on, basically knock all these little particles up into the orbit, essentially, of the asteroid. And so at the time, since it was such a big surprise, we didn't know how safe it would be to stay in orbit or whether we might actually be damaged and maybe lose the mission. So we had to do some really quick turnaround analyses by understanding the relative velocities of these particles, their sizes, and the team basically did a really heroic job to turn everything around quickly. And we did actually convince ourselves through simulations that it would be safe to remain in orbit. So that was obviously good news because we would have had to totally change our plans. It turns out that these particles, which range anywhere from like little like cereal flakes to coins to maybe the biggest are like billiard ball sizes, by having a team that we put together to analyze the longer term objects and try to understand their trajectories using optical navigation techniques, we were actually able to use that to get a good gravity model of the asteroid just from those serendipitous objects. And so we didn't have to go ahead and basically dedicate a whole new campaign just to get the gravity model. So it actually worked in our favor. So sometimes it does that. All right, so choosing our tag location. This was kind of a fun effort. We had about 50 sites from our initial sets of mapping images that we came up with. And then we, of course, have to find a way to down select that. And it's a combination of safety and what we call sampleability to be able to get to the spot and back away safely and actually have it be a very interesting spot from the science perspective. And we even had a campaign that we established with what we call citizen scientists, where they helped us to try to figure out which were the more interesting ones to try to sample. So we did several down selects until finally we got to the final 4 that you see on your screen here. And as you may know, the IAU has naming conventions, not just for planetary objects, but for surface objects, whether it be canyons or craters or boulders. And so we were actually able to come up with a clever naming convention for these final 4 sites, which are essentially bird types. And then we had to down select to 2. I should add, you know, our original plan for doing tag when we thought it might be just a sandy beach was to use what we call a LiDAR to basically slowly descend to the surface using those kind of echo returns. But because the surface was so littered with boulders and rocks and all the scattering effects that you get from that, we had to totally change how we would conduct our tag operation and switch to an onboard, what we call natural feature terrain technique, which includes like a hazard map so it can do an automatic back away. So a lot of these planetary missions are so far from the Earth that you definitely cannot joystick them. We have to contend with what's called a round trip light time, RTLT for short. And because it's so far away, you know, there's no way that you could react in real time. So you have to pre-program everything. And that includes having the onboard algorithms to be able to detect hazards and back away. So here's a little movie, a little GIF of our tag, which was on October 20th, 2020. And the way this technique worked is we had the sample canister at the bottom there, which essentially has a little flap all around on the inside of it so that any sample that gets stirred up and pushed into it, the flap will then close and keep it in place. And the way we stirred up the regolith, which is the scientific name for the dirt essentially, was with nitrogen bottles, which were attached to the arm. And so using the tubes, it could basically shoot nitrogen gas and agitate and stir up the surface and push it all into the container. The only problem was Bennu was full of surprises, and it was not a very hard surface. In fact, just the opposite. A lot of people liken it to a ball pit that you see that children play in. And luckily, we had the foresight to have a back away timer for our thrusters so that at a certain point after in the overall sequence, it would do a back away maneuver. And it's a good thing we had that because this is such loose soil, we probably would have just kept on going basically right into the surface if we hadn't backed away. So good thing to have contingency plans. So another surprise, we captured so much sample that it actually started leaking out. We have a camera on board that we call stow cam that was meant to take these kinds of pictures just to see if we could determine how much sample might be inside just from the lighting conditions. And we were shocked to see that all this sample was leaking out. So what we had to do was meet quickly as a team and determine what we wanted to do and whether it would be safe to actually stow this sample head inside the sample return capsule. By looking at the size of these particles that were streaming out, we determined it would be safe to do so. And so we pulled out our stow procedure, which wasn't supposed to be run for another couple days, I think. And we had to accelerate our plans and basically run that. The team did a wonderful job doing that, and you'll see in a minute here. Let me switch again to this movie. Except it's being covered up. Let's see if I can move this. All right. So this is what our tag looked like when we came down to the primary tag site. There's the nitrogen gas. We went more than a meter into the surface as some of the predictions, or half a meter. You can see the solar panels were in a unique position, so we had a sequence on board that would turn them in this configuration so that they wouldn't be damaged by any particles coming out. All right, let's switch back. All right, so here's what the SRC looked like. You can see we had a sequence that opened up the lid like a clamshell, and then we had little, what we call pyros, that would sever it essentially so that the lid could close again. And we took many pictures of the SRC over the years leading up to this just to confirm it wasn't being degraded by, solar radiation or anything else. So that was a successful stow, and you can kind of see there's that little bracket. There's actually 3 of them, so that as it pushes down, they hold it, they push back and then pop back out again to hold it in place. All right, so we had a series of maneuvers that we did for Earth return. All through this time in parallel, we have a curation facility at Johnson Space Center in Houston that was being prepared for the sample. We had a whole separate team dedicated to that, to making sure that was going smoothly. And then on September 24th of 2023 is when the SRC was released from, I guess, what you would call the mothership, essentially, and came back down to Earth and drifted over the Utah desert in what we call the UTTR, the Utah Test and Training Range. And you'll see in the following picture that it actually was blackened, which was expected from the reentry. And then the mothership executed what we called a divert maneuver to basically move away from the Earth so that it could continue on later for its extended mission. So let me switch to this movie real quick.
OSIRIS-REx is NASA's first asteroid sample return mission. It launched in September 2016 on a journey to explore a near-Earth asteroid called Bennu. After arriving in 2018, OSIRIS-REx spent nearly 2 years orbiting Bennu, mapping and studying its rugged terrain before carrying out its primary science objective. On October 20th, 2020, the spacecraft ventured to a small crater in the asteroid's northern hemisphere. It dodged jagged rocks and towering boulders and plunged its arm into the loose surface, excavating 6 tons of debris while collecting about 250 grams of material. OSIRIS-REx stowed its bounty and closed its sample return capsule. It bid farewell to Bennu in May 2021, embarking on a 1.2 billion-mile cruise back to Earth. Now, 2 years and 4 months after leaving Bennu, OSIRIS-REx is closing in on the place where its journey began. On September 24th, the spacecraft will approach to nearly 63,000 miles from Earth. It will power up and release its sample return capsule at 4:42 a.m. Mountain Time. The capsule must be jettisoned within a narrow time frame and at just the right angle to hit its target, an area of roughly 250 square miles in Utah's West Desert. Once the capsule is away, OSIRIS-REx will fire its thrusters to avoid colliding with Earth. At 8:42 a.m., the capsule will streak into the atmosphere at a blistering 27,000 miles per hour. It will race across the western U.S. and begin to glow with heat, allowing infrared trackers on the ground to chart its progress. As it pushes deeper into the atmosphere, the capsule will rapidly decelerate, subjecting the Bennu samples to a punishing 32 Gs. About 2 minutes after entry, it will slow to Mach 1.4 and deploy its drogue parachute, stabilizing its descent. The capsule will enter special use airspace at 8:46 a.m., almost 10 miles above the Department of Defense Utah Test and Training Range. Radar stations will lock on and track it to within 30 feet of its landing site. At 8:50 a.m., the capsule will extract and deploy its main parachute 1 mile above the ground. It will make its final descent at a leisurely 11 miles per hour, like a marathon runner savoring a victory lap, before touching down in the desert soil at 8:55. After ground teams retrieve the capsule, the Bennu samples will be taken to NASA's Johnson Space Center in Houston, Texas. The sample canister will be opened in the Astro Materials Acquisition and Curation Facility, and the samples will be curated, distributed, and studied for decades to come. Having delivered its cargo, the OSIRIS-REx spacecraft will depart Earth, but its journey will not quite be finished. In a daring encore, the renamed OSIRIS-APEX will enter an elliptical orbit of the Sun, repeatedly passing within the orbit of Venus and pushing the limits of its thermal design. Beginning in 2029, it will chase down and investigate Apophis, a 1,200-foot stony asteroid destined to make an exceptionally close flyby of Earth. After 13 years in deep space, at the start of a new decade, alone on a new world, the journey will continue.
All right, so that's a sneak preview of what we had coming next. All right, so hopefully a lot of you were able to see the live event for the sample return. It was very exciting. There was a little bit of heart palpitations when the drogue chute didn't open on time, but all the backup sequences worked perfectly, and the main chute opened up and was able to, of course, bring it down safely as planned. So here's just a picture. I think this was from the helicopter with the parachute, and you can see how blackened the SRC is now in this picture compared to when we saw the stow in space. So if anybody watched that live event, they had a lot of procedures in place for human safety. They had specialists that had to inspect the site, make sure there was no unexploded ordnances, for example. They also had to walk around and collect samples of the soil right around it, so that if any contamination had occurred, they'd be able to basically compare that and back it out because of that comparison. And so they had to get the SRC in place quickly and safely. They wrapped it in a special cargo net, and it was airlifted by helicopter to this special hangar so that it could be put under nitrogen purge as soon as possible. Again, the whole point is to keep the sample as pristine. And then it was airlifted to Johnson, as you saw in the video, and to the curation facility. One fun fact that you see on the bottom here, is postage stamps. So a lot of our NASA missions, we tend to do some collaboration with the United States Postal Service, and OSIRIS-REx was no exception, and we were able to come up with these really cool stamps. So if you ever get a chance, see if you can find those and maybe purchase them. So they did a quick look of the samples. There were several press releases around that. They had to basically get in this special chamber where you can only put your arms in with special gloves to basically get sample under analysis from the contact pads that you'll see in a minute, and just to get that quick look. And one fun fact, and they did this with the Apollo return samples as well, is a portion of the samples are always basically held in reserve for future generations to keep that pristine sample available for any new technologies that somebody might come up with, 20 or 50 years from now, and learn even more. So that's a fun fact. And then the video, of course, was before we returned to Earth, and it was just an estimate of the return sample based on just imaging from the cameras, but it was still double what the minimum was, so about 121.6 grams, I think. And so they do have a whole process in place for scientists around the world to request samples based on whatever they're trying to understand for their unique areas of expertise. And so that's ongoing as we speak and will continue for decades. And here's a quick picture of that very first sampling. You can see how it was basically spilled out a little bit from that inner flap in the interior section, and then you can see the contact pads all around the top. And then there was also these screws that you see. And it turns out that a handful of these screws, they could not loosen with the tools that they had. And so they actually had to delay taking the lid off by a few months until they could come up with new tools that would be that could fit inside that curation facility area. And so that was kind of a unique challenge. All right, so the last findings. This just came out a couple weeks ago. I don't know how we're doing on time, Deanna. If we want to do one more video, it's about 4 minutes, or should we skip over this one?
You're fine. You've got about 18 minutes left in your talk.
Okay, perfect.
Q&A.
So this is kind of hot off the press, if you will, just from the last few weeks. So let me switch over and play this last one.
The origin of life is one of the deepest mysteries in science, but the clues to solving it have been buried by plate tectonics, the water cycle, and even life itself. For answers, scientists are looking beyond Earth to primitive asteroids like Bennu, the target of NASA's daring OSIRIS-REx sample return mission. Now, material from Bennu is revealing a lost world from the dawn of the solar system, with the right conditions to foster the building blocks of life. When scientists examined the Bennu samples, they discovered evidence of a wet and salty past. Among the dark rocks were bright veins of salts that form on Earth when brines evaporate from alkaline lakes. Searles Lake, California is home to a mineral called trona, which is mined as a source of baking soda. Scientists found microcrystals of trona and other evaporite minerals within the Bennu samples, indicating that they once held pockets of sodium-rich water. Such brines are ideal for cooking up organic molecules, carbon-based compounds that are the stuff of life. Bennu is a carbon-rich asteroid, and its samples are chock full of organics, including amino acids and nucleobases. Amino acids can be bonded together in long chains to build proteins, which give cells their structure and function. Life is constructed from a set of 20 amino acids, 14 of which were identified within the Bennu samples. Nucleobases are the genetic components of DNA and RNA. All 5 nucleobases were discovered in the Bennu samples, a first for extraterrestrial material collected by a spacecraft. In addition to organic molecules, scientists found that the Bennu samples are surprisingly rich in ammonia. On Earth, ammonia is a common agricultural fertilizer. It readily evaporates at room temperature, but is more stable in cold environments, like those found in the outer solar system. Bennu is too close to the Sun to retain pure ammonia, so its samples must have formed during a more distant, frigid past. Salts, organics, ammonia. Thanks to OSIRIS-REx, we can now piece together these clues to tell a likely origin story for asteroid Bennu. 4.5 billion years ago, in the nascent solar system's outer reaches, a world of rock, metal, and ice took shape. Radioactive decay heated its interior, melting some of the ice. Pockets of mineral-rich water reacted with formaldehyde and ammonia to produce organics. As the water dried up, the dissolved minerals crystallized, leaving bright veins within the rocks. The world migrated closer to the Sun until it was shattered in a collision and destroyed. Bennu accreted from the rubble and drifted further inward, eventually settling into a near-Earth orbit where it could be reached by OSIRIS-REx. Our planet was bombarded by asteroids like Bennu early in its history, suggesting that many of the same organic molecules were present on Earth before the dawn of life. These findings help to close a gap in our understanding of the early solar system, but key questions remain open. Many amino acids can be created in two mirror image versions, like a pair of left and right hands. Life on Earth almost exclusively produces the left-handed variety, while the Bennu samples contain an equal mixture of both. This means that on early Earth, amino acids may have started out in an equal mixture as well. The reason that life turned left instead of right remains a mystery. Additional insights may come in 2030 when NASA's Europa Clipper mission arrives at Jupiter. It will hunt for evidence of a briny ocean within the moon Europa, an environment favorable to producing organics. Until then, scientists will dig deeper into the Bennu samples, unearthing more molecular clues about the origins of life.
All right. Let me switch this back. Just a fun fact for those that aren't aware, the Europa Clipper mission, which launched back in October, is actually a joint mission between JPL, Jet Propulsion Lab, and APL. APL was responsible for the propulsion module as well as the RF module for telecommunications, and several of the instruments like the EIS instrument, which is the Europa imaging system. And so we actually have an MSA here just down the hall from me, what we call Mission Support Area, which is the backup to JPL for interfacing with the Europa Clipper mission. So if anybody's ever here at APL and you're here for like a family day tour or something, you can check it out. All right, so we're almost done. Just a quick mention of the COVID years. Obviously, the timing was overlapping right on top of all the key events for OSIRIS-REx. When everything got shut down, we had to really come together as a team and figure out what we could do remotely and what had to be conducted with in-person participation. And we were able to do a really good job of doing almost everything remotely. We had to make some changes, some small tweaks to different tools and configuration files and networking and firewalls and things like that. But ultimately, we were able to find basically a good compromise where we could do it mostly remotely. TAG, of course, and the rehearsals was another story. We had to all be there, not just because of the importance of the event, but to just have practice being together, the rehearsal part of it. So anyway, in the end, it all worked out perfectly, and it was all because of everybody's dedication and teamwork. Just a quick shout out again to the team members. Here's just a list of some of the major awards that the team has won the last couple of years. In particular, the AAS Neil Armstrong Achievement Award and the Collier Trophy are pretty recognizable, and of course the Goddard Memorial Trophy. So kudos to the team for that. And I mentioned at the beginning of the talk that Bennu had to be given its name in the first place. And if you weren't aware, the Planetary Society had a fun contest back in 2013 to name the asteroid. They had over 8,000 entries, and the winner was actually a 9-year-old boy from North Carolina, Mike Puzio. And basically, he looked at mythology, Egyptian mythology. He was a fan of that, and books like Rick Riordan, you know, Percy Jackson, those kind of books. And he came up with the idea of this heron, which in mythology was named Bennu, because he thought the spacecraft looked like a heron with its solar panels out like wings and the tag arm looking kind of like the legs of a heron. And so we met in Houston during some of those sample return events and started talking about maybe writing a picture book together to basically talk about his side of it with the naming of the asteroid and then my side with the operations. So we got a first draft out, and hopefully later this year we'll be able to find a good publisher for that. Another fun trivia is Brian May of Queen. Those of you that like rock and roll might recognize the name. He's actually a co-author of this fun book. He's a team member on the OSIRIS-REx mission, and one of his areas of expertise is captured in this fun book, which I have a copy of here as well. Not sure if I can show it or not. You can almost see it. Anyway, you can see a picture of it there on the right. And if anybody's really interested in seeing these images of asteroid Bennu really pop out in 3D, definitely encourage you to try to find this book. And I have a link here which has a fun interview with Brian May for anybody that's interested, where he talks about his technique of how he does this stereo imaging. All right, we're just about out of time, so what's next? The name was repurposed to APEX, which stands for Apophis Explorer. And it certainly wasn't a slam dunk by any means. We had to make sure that all the instrumentation survived tag and could actually support an extended mission. And we had to figure out exactly what the spacecraft would do to make it a worthwhile mission in its own right. And so we basically had a whole bunch of meetings and reviews. And then ultimately, I was part of the review team for that, which was certainly my honor. That was after I had already left the team. And then in 2022, it was officially awarded. And here's a fun poster that shows OSIRIS Apex. So after we had that divert maneuver, about a month later, we had the first maneuver that would direct the spacecraft towards this asteroid Apophis. And the team actually then split, basically, where the core sample analysis team remained with OSIRIS-REx, and then the other half of the team for operations transitioned to Apex. And one fun trivia fact here is Danny Della who's the PI for Apex. She started out many years earlier as an undergrad student and basically worked her way up the ranks over the years all the way to Apex PI. So that was really cool. But in short, all the instruments did survive tag. There was just very minimal degradation. And as you saw in the one video, it requires multiple what we call perihelion passes close to the sun inside the orbit of Venus. It was never designed to operate that close to the sun where it gets so hot. And so the team had to come up with real clever ways to basically put the spacecraft in different configurations that would minimize heating spikes. And so far to date, we've had 2 perihelion passes and everything survived those as well. So fingers crossed that all the remaining ones will work, and then we'll get to Apophis in 2029. I won't go into these in too much detail. You can read all about Apex, but essentially there's this huge asteroid Apophis that was mentioned in the video. Definitely be on the lookout for it. 2029, it'll be so close to the Earth, we'll be able to see it with the naked eye, which is pretty amazing. This was at the top of the chain for potentially hazardous asteroids until refinements showed that it wouldn't hit the Earth in 2029, thank goodness. But anyway, we took advantage of that proximity, and we're basically going to approach it and study Apophis, and then basically do a gravity assist and loop back around a year later and do the more in situ observations, including what we call air tag. So we no longer have a sample canister, of course. So what we're going to do is come down to the surface and fire the thrusters just like we did for that backaway maneuver and stir up the regolith to see what's underneath the subsurface. And just a little more fun facts about Apophis. It's a S-type asteroid rather than B-type or C-type. It is the most common in the stony class, and so we want to really learn as much as we can. And there are other missions that they're proposing to go visit Apophis in 29. All right, so just a fun take on There and Back again from Lord of the Rings. You can see the mark we left on Bennu when we departed. This was from that flyby that we did after tag. And by the way, that was not in the original plan. We had to have a lot of meetings to convince ourselves it would be safe to do that since we had already collected the sample. It was a little bit controversial, but we were able to show that it was safe to do so. And that's my talk.
Okay. Well, thank you very much. We've got
Absolutely.
5 minutes for questions. And so there's one in the chat from Martin. This ball pit composition, I've also heard that referred to as a rubble pile.
Right.
Do you think it's held together by gravity or some other adhesive force? Do we have theories about how common it is?
Yeah, so you saw the movie that talked about the rubble pile being a reaccretion, if you will, after some kind of collision event. And in the early days of the solar system, and it was a lot more common than it is now to have those kind of collisions. So we think there's a lot of objects out there that are like this, basically rubble pile of form. Yeah, it is a combination. Certainly, it wouldn't have accreted at all if it didn't have enough gravity to hold its form. So gravity is, of course, a big component for that. I'm certainly not a scientist. I'm an engineer, but I'm sure it's a combination, of the gravity as well as, lower level effects that keep it in place. But I'll be happy to do some more research on that for Martin.
Okay. I had a question that's just my own because we're talking about communication here. And I'm wondering how important are animations like the ones you showed us for communicating mission goals and results, and also for getting funding in the first place?
Yeah, public outreach is a huge part of what we do. For example, the extended mission and new missions, they're not going to be successful when they put in their proposals unless the public is really engaged and interested, and that comes from previous missions and all the work that we do in that area. So yeah, I think animations, it's not so much for mission operations as much as public outreach. We have our own kind of in-house tools that we do for more precise ways of visualizing the spacecraft. We do in some cases have virtual reality, for example, where we can manipulate and rotate the spacecraft around and see exactly where different instruments are positioned. We also have tools, planning tools, where we can look at the field of view of different instruments and see what kind of footprint it would have on the surface of an object, and to decide whether we need to do like late updates for it and so on. So those are the kind of tools we use in-house, but these kind of animations that you saw on YouTube are very helpful for just getting the word out and basically to boil it down to a presentation that anyone can really understand and enjoy and appreciate.
There's another question in the chat, but you made me think of something in our next presentations on music. You mentioned Sir Brian May, and we have a lot of APL friends. We had Alice Bowman here. We've had Louise Proctor. We had Deb Chattopadhyay recently.
Terrific.
And we haven't had Brian May, although if you could put a word in, we would like to. But is there a reason he wrote a song for New Horizons and doesn't seem to have written one for OSIRIS-REx or OSIRIS-APEX yet?
That's a good question. There might actually, I left the project in early 2021, so it is possible there's a song out there. I actually haven't searched for that, to be honest, but there's no specific reason I'm aware of. But yeah, if anybody in the audience has heard of that, I would be interested to find out, and I'll do a little search when we're done. But yeah, it's really amazing to work with him. He's basically astrophysicist emeritus, if you will. So he's very knowledgeable in these kind of techniques. And you mentioned Alice Bowman, so he supported the New Horizons mission as well, which went to Pluto. I was part of that team, fortunately, as well, for the flyby in 2015. And then subsequently, we had a flyby of another Kuiper Belt object called Arrokoth. And so Brian May had the same kind of techniques that he applied there. Except here, he took it to the next level. You saw the one movie that talked about the resolution that we captured of this object is finer than any other that we've explored, including the Earth itself. And that's, globally mapped. And so he had a lot of really good images to work with for this technique and for that book. So.
And just to wrap up, last question is kind of a combination. One person said, what's the one place he'd like to go next? And somebody else said, what's the next mission? So I guess, what would you like to have happen next, and what is next?
Well, at APL, planetary defense is a big part of what we like to do. A lot of you may have heard of the DART mission, the Double Asteroid Redirection Test. And then, of course, in all the news lately, there's this new asteroid discovered in December, which is potentially hazardous. And we have, I think, Hubble and James Webb will be imaging that later this year in March and May to refine its orbit. So keep an eye out for that in the news. But yeah, those kind of missions, planetary defense, are pretty exciting. We want to practice all different techniques, just in case we ever have to use them. The DART mission was an impactor technique. We were able to confirm that we could nudge the trajectory of a small moonlet, if you will, of an asteroid by about 30 minutes. So we were able to change its orbit by that much. So it's a proven technique, but just one of many. But Apex will be very exciting. As long as it can stay healthy through those perihelion passes close to the sun and doesn't overheat, then it's going to be really exciting to study Apophis, especially in relation to being able to see it in the sky with the naked eye and knowing that we're studying it. That's a pretty cool correlation there. Yeah. So any missions coming up for these kind of objects, who knows, in the future we might have mining missions and things like that, from the private sector. So we're just at literally the tip of the iceberg for visiting these types of objects. So it's exciting. Glad to be a part of it.
Yeah, definitely. Very glad to have you be a part of it. I really appreciate your time. Fantastic presentation and wonderful visuals.
Okay.
And I thank you very much for participating in Roger That. So say hi to everybody, and I will try to get to one of these friends and families days.
Absolutely. I can be your friend, guest host.
I have eaten in the cafeteria, so I've gotten that far.
Okay, right. And if anyone has follow-up questions, feel free to compile them and send them to me offline. I'll be happy to respond to them. So.
Right. Thank you. Yeah, if anybody wants, are you open to having your email address shared, or do you want me to compile them and send them directly?
Sure thing. And just some quick searches on YouTube, you can find all these kind of videos. There's a lot of really good information out there, especially the ones that Goddard Space Center compiled.
All right. Well, thank you so much. We're going to take a little break and be back at 1:30 with Joni Green and music and space. Thanks so much.
It's been a pleasure. Thank you.